Welcome, everyone, to another edition of our Liftoff webinar series. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs here with Lyft. Thank you for taking time to join us today and joining Flow 3D to speak about their fluid dynamics for additive manufacturing and laser welding analysis and optimization. We're looking forward to hearing Lisa's presentation in just a second. I do have some housekeeping items to go through before we get started. This webinar is being recorded, so if you can, you should be all on mute, but if you are not, please put your devices on mute to the best of your ability. That will avoid any background noises and any interruptions during the presentation as well. The presentation will be available on our website at lyft.technology a little bit later on this afternoon, so if you're unable to stay for the whole thing or understand there may be folks you want to share it with, please do so. And that'll be available a little bit later. Finally, we will be hosting a Q&A session after Elisa's presentation as well. So please use the chat function or the Q&A function that is available via the Zoom taskbar or the Zoom menu bar. We're all very familiar with Zoom these days. So hope everyone is remaining safe and well. But in the meantime, we'll keep doing these virtually, and you can use the Q&A session, so I will facilitate those afterwards. But you can send in a question at any point in time during the presentation. I do want to share a little bit of information about Lyft before we get started. So Lyft is a public-private partnership, nonprofit organization based here in the city of Detroit. We are a public-private partnership between industry, academia, and government. We are one of 16 national manufacturing innovation institutes around the country. And our goal at Lyft is to drive American manufacturing into the future through technology and talent development. And we do that through what we are calling smarter manufacturing, because we understand that the future of our national economic security and resiliency rests on the manufacturing sector. And we want to make sure that it is the United States who takes the lead on that, because whoever comes out with smarter manufacturing first will take the lead, and we want that to be here at home. So what do we mean by smarter manufacturing? Well, at Lyft, we look at the connection between materials, processes, systems, and the virtual systems and the talent that it takes to run all of these. So we're talking about materials research, manufacturing process, and virtual systems. So at Lyft, we run two programs. The first is our technology program, Leading Innovations for Tomorrow, and our talent program is Learning Innovations for Tomorrow. Let's put those two together, and you have Lyft. So a little bit about the technology program. These are our technology pillars. All of the work that we do at Lyft falls underneath each of these categories in some way, shape, or form. All the way from integrated computational materials engineering to agile, smarter manufacturing, alloy process development, and multi-material joining. A little bit deeper dive into some of these pillars. I'm not going to get into each of these, but if you have questions, would like to speak with someone on our team about any of these, please give us a call, shoot us an email. We'd be happy to reach back out to you and see how we can help. We can help you take your idea from concept to commercialization, further optimize it, whatever we might need to do to help you advance your technology. On the talent side of the house, it is still about innovation, but it's more about learning tools, new pathways, new venues. We offer a program, for high school students called Ignite Mastering Manufacturing. That is offered at our Lyft Learning Lab, which is in our facility, perched above our Lyft high bay. So the students come into our facility. Pre-COVID, we had 100 students a day from local high schools come and participate in the curriculum, hoping to get them back here as soon as possible. But students get to look out and see all of our technicians working on some of the innovations that we just referenced earlier. So very excited about that. We also offer our own certification courses in some of the most in-demand jobs that are available in advanced manufacturing, CNC, welding, industrial technology maintenance, and the fastest growing field, which is robotics. We also offer those same majors through a program called Operation Next, which is growing across the country as well. This is especially near and dear to our heart because it was formed as a pilot program for separating service members of the military down at Fort Campbell, Kentucky. Before they separated from the military, we gave them the opportunity to earn a credential, industry recognized, nationally portable credential in those majors. So when they left the service, they were able to go get a job in industry immediately. 90+% success rate with that program is growing around the country and is now available to the National Guard and reserve members, along with their spouses in Michigan, in Wisconsin, in Florida, where we've expanded the program beyond Fort Campbell to the Hampton Roads region of Virginia. And stay tuned for announcements with Alabama and New York as well. So looking forward to that program expanding around the country. I mentioned we are a nonprofit public-private partnership. We're also a membership-based organization. So what do you gain from being a membership? Gain from being a member at Lyft? All the things you see on the screen here. Trusted advisor. We have not only our experts in-house, but across the ecosystem, and you're hearing from one of them today. We are a technology accelerator, moving exciting technologies to commercialization to help it move the needle in advanced manufacturing. We are a technology showcase, showing the art of the possible. Invite you all to see our facility in Detroit next time you are in town. We'd be happy to show you around all the things that we have going on here. And across our ecosystem. We are a connector and a convener. That's why we're all here today. So thank you so much for joining us. A talent developer, I mentioned earlier, from the high school ranks all the way to adult learners to help people gain, begin their career, advance their career in advanced manufacturing. And finally, we are a government partner. It can be unruly and unwieldy to work with the federal government. We know that, especially for small, medium-sized companies. So we can help you navigate that and help you become a part of that ecosystem, because we know that is where a lot of innovation takes place, is at the small and medium-sized companies. So that is Lyft in a quick nutshell. Please, I encourage you to follow us on our social channels, give us a call, shoot us an email like olden times, or visit us on the website. I'd be happy to answer any questions for you. But in the meantime, I'm going to turn it over to Elise from Flow3D for her presentation. So Elise, the show is yours. Second to get your screen up. There we go.
I'm on mute. There we go. All right, thank you. Yeah, I'm very excited to be here today, and I'm excited to learn about all the new stuff going on with Lyft. So thank you all for joining us. So what we will focus on is computational fluid dynamics for modeling additive manufacturing and laser welding processes using Flow3D AM. So our agenda is pretty simple. We'll look at an introduction into Flow3D, look at some case studies from industry and academia that have been using this software for AM and laser welding studies. And we'll do some overview of features, capabilities within the software, and we'll also discuss a bit on workflow automation. So just to give you kind of a baseline understanding of what Flow3D is, it's a CFD software specifically designed to and suited for free surface transient flows. So it's based on the volume of fluid method, which in a nutshell is a computational method for tracking the evolution of the free surface. So where you have a sharp gas liquid interface, and it's utilizes the concept of a fluid fraction. So when you have a computational cell entirely filled with fluid 1, it'll have a fluid fraction of 1. Conversely, if it's entirely void or filled with your gaseous material, it'll have a fluid fraction of 0. And any intermediate value is where you know there's a presence of a free surface. So it's a very robust method for these highly transient sharp interfaces. And that's at the DNA of Flow3D. I'll also mention Flow3D is of course based in Navier-Stokes, but on top of these numerical schemes we've built on a wide range of different multi-physics capabilities. So for today's applications, we're primarily focused on phase change, heat transfer, surface tension, viscosity, solidification, things of that nature, but we've got a ton of other multi-physics capabilities for other applications as well. And the products so we have a family of products under Flow3D that relate to different application areas. And the products, of course, for AM and welding are going to be Flow3D AM, Flow3D Weld, and then Flow3D Post is our post-processing tool that you'll use for doing any sort of analysis, creating visualizations, things of that nature. So to give you an understanding of what I mean by free surface flow in practicality, here are a few examples. So we do a lot of work in water and environmental hydraulics type problems. So we've got lots of transient nature going on there, turbulence, whatnot. We also have a long history in modeling metal casting processes. So that's a low pressure die casting simulation there on the bottom right, capturing early freeze defect that was also seen in the shop. And then we also have a lot of experience in microfluidics applications, so surface tension driven flows like inkjets or coating applications. And all of this experience has lent itself into our more recent endeavor in the last 5-6 years or so in additive manufacturing and laser welding, such as laser powder bed fusion there in the top left. So to capture laser material interactions in these laser-based manufacturing processes, we do need to account for some additional physics. And those are going to relate to thermophysical material properties, laser heat flux distribution, different processing parameters. So we define the laser heat flux distribution just as it is in reality. So we account for the beam, spot diameter, wavelength, focal distance. So really anything that you're working with, there's a lot of flexibility in how you can set that up in the software to accurately represent that distribution. We also have the ability to really implement any type of laser motion that you can think of. It can be brought in as a CSV file if you're working at an angle, if you're doing some kind of new path design for optimizing microstructure or remelting, getting rid of void formation. It's all completely up to the user how you want to specify that beam motion. We account for shield gas pressure as an additional pressure force on the surface of the material based on the shield gas density, velocity. So that's accounted for. Usually that comes up more in DD cases, maybe a little bit in laser welding. And then evaporation pressure is extremely important, also referred to as recoil pressure. So this is yet another additional pressure force on the surface of the material, and it's due to the rapid vaporization of the material as it's melting, and it can lead to keyholing, it can lead to morphology in the melt pool. So that's an important phenomenon that we account for. And then lastly, multiple laser reflections. We do this via ray tracing, and it's important during keyhole welding where the multiple laser reflections will affect the effective absorption of the material from the laser. So we'll dive into some additive manufacturing, but really all of these physics for the most part lend themselves into the laser welding space as well. But we've got some examples here of AM, modeling AM processes. So as all of you, I'm sure know, additive manufacturing is a very complex process. It's ultimately a multi-physics phenomenon. We're dealing with heat transfer and phase change and Marangoni effects, laser reflections, recoil pressure. So all of these things work together to lead to your final solidified part. And these can all be alloy dependent as well. So when you're working with different materials, or if you're exploring different processing parameters, working with different machines, there's a lot to consider. It can be very labor intensive when you're trying to analyze all of this using experiments alone, which is why we often look towards modeling. So when looking towards modeling to capture these processes, create digital twins, do kind of end-to-end process analysis, Flow3D AM is one important piece of that puzzle, in that what we're really looking at is the micro and meso scales. So micro being the particle scale, where we're looking at recoater blade interactions, powder compaction, particle forces. And then at the meso scales, we're looking at melt pool dynamics, porosity formation. And these results can be used to inform microstructure type analysis, and can also be used to inform part scale analysis, where these are typically based on FEM type frameworks, where you're looking at part scale thermal distortions, residual stresses, but you're no longer accounting for all of the fluid flow, which is what we focus on with the CFD side of things. So to give you an idea of how this kind of breaks down, for laser powder bed fusion, when we go through this modeling workflow, we start with powder settling and spreading. So we account for the powder distribution, any sort of cohesive, adhesive effects within the powder. Maybe it's due to moisture, electrostatic forces. And ultimately what we're trying to get is that final powder compaction in the powder layer that we can then perform the melting simulations on. So once we've completed this step, this is using the discrete element method. Then we extract that result into an STL, and then we do the melting simulation, where we are preserving all of the voids, all the packing fraction from the powder side of things. The only limitation here is that we aren't accounting for powder movement as it relates to convective currents in the gaseous phase in melting, which can be important, but all of the other phenomenon due to Marangoni effects, keyholing, solidification, cooling rates, all of that is captured in these melting simulations. So we're still getting very good information about the effective processing parameters on the result, despite the fact that we're not quite accounting for that powder movement just yet. And then ultimately, so we're still working in the mesoscale range. So we can do a few different layers. There is a limitation just in terms of computational efficiency. And as time goes on, I'm sure that will improve. But right now we're looking more at 3 to 5 layers, kind of domain size. And we preserve the thermal history from each previous layer, so that the subsequent layer, we're seeing the effect of remelting, any sort of void formation or mitigation. There's a lot of phenomenon that happens as you build layer over layer, as you would, I assume, guess. And that is all something we can capture in these melt pool simulations within a few layers. And then you can take it over to your FEA tool and ignore the fluid flow and kind of do the part scale build. So one of the kind of key defects that I think everyone is always looking out for is porosity formation. Often this is a result of operating in a keyhole mode. So researchers at DTU did a numerical experimental study where they were qualifying the transition into keyhole welding and looking at the mechanism that leads to porosity formation from keyhole welding. So they used a KU11 in-house KU11 machine. They ran their experiments, and then they replicated the experiments with a numerical model and compared the results. So when looking at these simulations, we can get a very good understanding of what is happening at any given time during this process, and what the mechanism that leads to porosity is. Once we transition into keyhole mode, you'll see this large kind of keyhole opens up, and there's both recoil pressure, higher recoil pressure at the bottom of the keyhole, because that's where most of the heat is concentrated. And then because of the higher temperature at the bottom of the keyhole, we're going to end up with lower surface tension pressure. And conversely, at the top of the keyhole, you have higher surface tension pressure. And this can form a cold zone, which can lead to momentary keyhole collapse, which is what leads to the initial pore that gets trapped in the melt pool. Once that pore gets pushed backwards from the strong downward flow in the molten pool, it'll round off due to hydrostatic pressure. It may be released at the top due to buoyant forces, but in some cases it's trapped by the advancing solidification front, and that's what leads to the porosity in the final part. So what's notable of this study is that these researchers compared both the depth of the resultant pores as well as the diameter between the simulations and the experiment. So if you look here on the graph on the right-hand side, the data in black is the experimental data, and in red is the numerical data. So we can see very good agreement in terms of where those pores are respective in the depth of the part, as well as the size of them. Good agreement between the numerical model and the experiment. Now, printing on overhangs is another area of interest that's been coming up more recently for us. I'm sure many people are looking into how you can print more detailed geometries, how you can go from one media to the next without leading to different kinds of defects that come with that territory. So in this example, this is just a kind of a sample case of printing on an overhang where the first two tracks are on the solid base material, and then the third track is where you're going on the overhang where it's primarily powder. And then we're looking at the difference between a 45-degree overhang and a 30-degree overhang. And what we can do in Flow3D AM is extract the melted region, and then we can look at the downskin surface roughness to see what kind of fusion conditions we're getting, what kind of surface roughness we're getting. And so you can see in the comparison of the two here that the 45-degree angle did lead to more surface roughness, lack of fusion, while we get better conditions for the 30-degree overhang, which depends on how much flexibility you have in your design. But there's things that you can analyze from a modeling perspective without having to make these parts out every time. So researchers at DTU did a full-scale study where they looked at dross formation in printing on overhangs. So a different scenario from the previous case in that in this case, they're actually operating in keyhole mode. So once they hit the edge of that dense region and get into the powder region, well, for one, the thermal conductivity in the powder region is a lot lower because there's less contact between individual powder particles. And so the conduction, the ability of the material to conduct the heat away is also lessened. And you get a lot more heat retention locally once you hit the powdered side of the domain. And this leads to what they call dross formation, where you get this sort of drilling effect as you go over the edge from the dense to the powder material. And that can lead to undesirable fusion conditions and other defects that are we're trying to avoid when going from one media to the next. So qualifying this, understanding what are the forces at play that are leading to this, what can we do to mitigate dross formation and create a more consistent print when you're going on to different medias. What they have proven through numerical models is that with high energy density, so think higher power, lower speed, you're going to have recoil pressure dominant forces, and that'll lead to more keyholing. While when we have lower energy density, so lower power, higher speed, excuse me, that'll be more capillary and Marangoni effects will be more dominant in that scenario. So that's kind of what we're trying to gain. You have better process control when you're operating in the sort of Marangoni dominant realm for the most part. So the proposed methods for mitigating this dross formation when you're going from one substrate to the next, beam shaping, which we'll look at next, power modulation, so turning down the power when you get to the powder layer, or speed modulation, so speeding up your laser, and that way you can avoid that drilling effect once you get to the overhang. And you can see from the experiments, they did a kind of quality check in terms of, do the simulations and the experiments agree in terms of the conclusions made, which there was good agreement here as well. So looking into beam shaping, which is, I think, becoming more attractive as a way to increase process stability and have a little more flexibility in terms of how you're printing. So what does it help with? Melt pool dynamics, having a more quiescent melt pool, having lower velocities just in general, and mass flux and vaporization. So we do want to kind of lessen this as much as possible. When you have high mass flux and vaporization, you're going to have higher recoil pressures, and that can lead to spatter, porosity, as we saw in the previous example, and some other issues. So beam shaping is a good way to increase process stability. Ultimately, process stability is useful for getting the desired material properties in the final part. So we want to have better control over thermal gradients, less residual stress, better microstructure control. So all of these things are a little bit easier to maintain when you have more flexibility in your heat flux distribution. And then productivity as well. So when you're increasing the area of your heat flux distribution, oftentimes this can lead to printing over larger areas, increasing your scanning speed. You can also have more optical flexibility with beam shaping, especially with some of the new technology that's coming out with in situ kind of beam shaping techniques, defocusing, things like that. So what we've been doing on our end is working with Enlight and Econity. So Enlight is a laser manufacturer, Econity is a machine manufacturer, and we've all been collaborating to run simulations for the AFX ring mode laser created by Enlight, and compare that to traditional Gaussian distributions and look at what are the effects in terms of the relevant forces at play, the ultimate kind of thermal stress evolution and microstructure, cooling rates and things like that. So in setting up these simulations, of course, you always have to start with a validation. So we ran simulations for the Gaussian distribution and the AFX ring mode. Econity provided us with cut cross sections from their experiments so that we could compare the width and depth with simulation and experiment. And then in doing that comparison, we can see that there is good agreement between the Flow3D AM simulations and the experiments provided by Econity. And qualitatively speaking, I will mention that we've done a pretty intensive webinar on this topic exactly. So I won't go into too much detail today, but just on an overview kind of summary of what the findings were, is that we can see from the experiment, if you look at the AFX ring mode here, the velocities in the melt pool are much lower than in the Gaussian distribution, which of course is going to lead to less spatter probability, just a more quiescent melt pool, less transition stages. And similarly, the mass flux due to vaporization is much lower. So that's going to lead to less spatter, again, lower recoil pressures. And you can see from the experimental images here that the Gaussian distribution did indeed produce quite a bit more spatter than the AFX ring mode. Switching gears a little bit, we're going to look at two material printing and joining. So of course, that's an important aspect of manufacturing. Can we bond two materials? Can we mix two materials? How do we model this, understand this without entirely relying on experiments. So in Flow3D AM, we can look at 2 independently defined alloys. So all of their thermophysical properties are independently defined, surface tension values independently defined. And there's different ways we can approach this. So laser powder bed fusion example here on the left, we have evenly mixed copper aluminum alloys, and then we're just melting them. In a directed energy deposition where we have a powder or a wire feed that's being deposited onto a substrate, we can model mixed powder in the powder feed. We can look at having a different material as the substrate versus the powder feed, say if you're doing repair work in a cladding setting or something to that effect. So there's a lot of different ways that you can employ the 2 materials, but being able to capture their effects independently as they're joined together is extremely useful. So in this study from researchers over at GM, they looked at laser welding aluminum and copper in a lap joint configuration. And what's important here is that you get sufficient mixing so that there's sufficient fusion between the 2 alloys, but too much mixing can result in detrimental intermetallic compounds. So finding that sweet spot, finding the threshold, and identifying the process parameters that are going to lead to that kind of place where we have sufficient fusion, avoiding the intermetallic compounds. We need to understand the effects of these processing parameters on the mixing, and modeling is a super convenient way to qualify that and look at the quality of the mixing at a very detailed level. So looking into their validations, what they compared was the EDS element mapping from experiments with simulation results from Flow3D AM. So if you look at these images, experiments on the left, simulations on the right, and what they're plotting here is the copper weight percent. So visually, we can see very good agreement between the 2. And they also looked at the concentration of copper at any given point along the X and Y axis, comparing simulations and experiment, which in both cases we have good agreement as well. And what they found was that copper concentration above 50% at the top of the molten region was leading to increased cracks in the fusion zone. So they were able to use the simulations to identify processing parameters that would lead to sufficient fusion, but not reach that 50% threshold that would lead to cracking, so that they could optimize this process of joining the 2 materials. I'm going into a bit on directed energy deposition, since I just gave you a taste of that. What we can do, as I mentioned, this can be wire or powder feed based, or both. There's some interest in hybrid systems. There's benefits to each wire or powder, but by combining the 2, you can kind of reap the benefits of both. So there's some interest on that side as well, and we can look at that using computational fluid dynamics. And then we can also look at multi-layers in DED. So DED is a little bit more flexible in that the simulation runtimes are a little bit faster than, say, laser powder bed fusion. So we can look at a few different layers. The track width, the track lengths are a bit bigger, more in the few millimeters rather than usually less than a millimeter if we're doing a laser powder bed fusion simulation. So there's a lot of information to gain from modeling a DED process. And in this study from researchers at DTU, they were looking at the effect of the powder feed, the velocity of the powder feed on the melt pool dynamics in marging steel, where the phenomena of interest is very much the same as other cases: Marangoni effects, recoil pressure, heat transfer, things of that nature. But something to point out here is that even when we're working with a powder feed rather than using the discrete element method to do powder spreading like we do for LPBF, we're still accounting for the powder distribution as it is in reality. And then if you have mixed alloys, as I mentioned, we can account for that as well in the powder feed. So in this case, they did a few different layers. So you can see there's quite a bit larger domain size that you can achieve when you're doing a directed energy deposition. Plotting the temperature here, so you can see as the powder particles come down and are melted by the laser, you can see their temperature heating up. Looking into their validation, you can, what they did was compare the width and depth of the solidified bead, as well as the melt pool dimensions during the process itself. So looking at their comparison of the width and height of the bead, the error percent was about 2.4%, 6.9%, which is pretty good agreement in terms of comparing experiment to simulation. And what they found was that the higher carrier gas velocity, it leads to an increased height to width ratio because of the less contact time that there is between the particle, the powder and the lasers when they're working with a higher carrier gas, because the powder is coming down much faster, being melted faster, so there's less contact time. And then they also found that the track wettability will decrease when you have an increased carrier gas velocity. So this all comes back to whether Marangoni effects are dominant, whether recoil pressure effects are dominant. But you can see from the images here, this case at the bottom is when you have higher carrier gas velocity. So we've got much higher Marangoni vortices, and you can see that there's a wider track width, but less depth. And so when you have a lower carrier gas velocity, you're going to have higher width, less depth. So what's important takeaway from this study is that track morphology and production rates can be manipulated by the carrier gas velocity. So usually we're looking at power or speed to kind of change the dimensions of our tracks. But in directed energy deposition cases, we have that additional parameter that we can look at, just the speed of the carrier gas velocity, which has quite a big impact on the morphology of the track. So some useful outputs that we can look at as well. We can visualize the beam profiles. This is useful for understanding the laser material interactions visually. Also kind of a sanity check when you're doing your simulations, make sure that your laser is oriented correctly, defined properly. If you have it at an angle, things to that effect, it's very useful to be able to visualize the beam in the simulation. And then we can also output the melt pool dimensions. So height, width can be extracted automatically. And you can use that when developing process windows. You want to understand, what dimensions you're getting. You can also use it as an optimization parameter, which we'll talk about a little bit here at the end. So that's a useful output in terms of just understanding immediately what effective dimensions you're getting. And then we can also extract the melted region itself, as I mentioned earlier. And this is useful in understanding the effective part density, doing porosity calculations, understanding surface defects and morphologies. So there's a lot of information that can be gained just from extracting that melted region and neglecting the unmelted powder. And then we can also extract temperature gradients, cooling rates. So these are the outputs that are typically used to inform the next leg of analysis, whether it be microstructure, thermal stress evolution. So those are outputs that are readily available to you. And to give an example of taking the CFD results over to an FEA analysis, researchers at National University of Singapore, Wen Tao Yan's group, they developed an in-house custom FEM model, and then they mapped the thermal fluid simulation results into their FEM model to understand thermal stress evolution for a few tracks. So you can see from the results here, by plotting tensile and compressive stress, you can see that where voids are forming, we're getting higher tensile stress values. So that's good indication if you're seeing high tensile stress in your FEA simulations, then you can reasonably assume that that's going to be the location that cracks will form if they do. And then we can also understand the effect of a few different layers. So once you deposit a second, third layer, you'll have some remelting. Some of these defects will be fixed. Some of them will be accentuated. So there's a lot of information to be gained from simulating a few tracks and then doing the thermal stress analysis on that part. And then we'll touch lastly on a bit of workflow automation. So as I've mentioned a lot during this presentation, a lot of the interest is in process parameter development. It can be for new alloys, more commonly used alloys, but a new application. There's a lot that goes into kind of qualifying the process parameters and understanding the effect of different combinations. So using melt pool models to do this, as you've probably inferred so far, we start off by doing a validation, compare with experiments, make sure everything looks good. Then you can do simulations of different process parameter combinations. And ultimately, we're trying to develop that process parameter window to identify those parameters that will lead to conditions which are favorable and which will lead to conditions which are unfavorable, and we should probably not use those parameters. So there's lots to consider here. Laser power, scan speed, heat flux distribution, whether you want to be in keyhole mode, conduction mode, what kind of atmospheric conditions you have, what are your material properties that you're working with. So doing these types of parameter studies for a variety of different alloys can certainly add up, especially when you're dealing with experiments alone, but also when you're doing kind of an iterative approach with simulation. So the way this works from a simulation perspective is you set it up, you run it, you do your post-processing analysis, you go back to the original setup, you iterate on the parameters, and then you kind of go through again and again, which definitely saves time in general, but can be a bit cumbersome when you're wanting to test 50, 100, different combinations. So what we've developed is a tool called Flow3DX, which is used for automation and optimization. And you can just import all of the parameter combinations that you want to test into the software, or you can put them in manually. And then you'll set up a simple workflow where you have certain input conditions that you're interested in studying. And then certain outputs, say you want to look at melt pool dimensions, you want to look at porosity formation, you can choose that as your output metric. And then you just run these simulations, you hit go, the software will go through each parameter combination that you've specified. There's no need for you to go in and manually set up each input file. And then at the end of the day, you get all those results as well as animations or images if you want to tie it to our post-processor. So it really saves a lot of time when you're trying to develop these process windows. So in summary, we've really found that CFD simulations are providing valuable insights into these processes, and that really relates to both the AM side of things, laser powder bed fusion, directed energy deposition, as well as the laser welding, where in the case of AM, you want to look at powder compaction, spreading, powder interaction. In both cases, you want to look at melt pool dynamics, prediction of defects. We want to extract relevant information to use in subsequent models such as microstructure prediction, residual stress analysis. And then using workflow automation, we can develop these process parameter windows or welding schedules in a very efficient manner where, we're able to tie it all together and provide some valuable insights into how to bring these processes into production. And that's what I had for you. Here's my contact info. I think Joe might mention as well, but any questions, happy to answer.
Yeah, thank you so much. That's a lot of information. Certainly appreciate the presentation. I'll let you get a drink of water for a second, and encourage folks to follow up directly with Elise if they do have questions or like more information. We do have some time for some questions today. So if you do have a question, please go ahead and use the Q&A function that is available via Zoom here, and we can get as many of those asked as possible. Are there particular industries that you're working in more than others? Just out of my own curiosity, which industries are most prevalent with folks you're working with?
Yeah, I think aerospace folks tend to be kind of on the cutting edge of AM research. Automotive are more interested in the laser welding side of things. Lots of academic interest. There's there's a ton of researchers in academia that are looking into these modeling. That's I would say the biggest players, maybe a little bit of medical device for micro welding and stuff like that. And then the EV side of things, batteries.
Right. That's many of those industries are on the call, I'd imagine, here today, and members of Lyft, and obviously I mentioned the automotive industry being here in Detroit. That's certainly an area that we are very familiar with. So a couple of questions that have come in. Can you model non-spherical powder, like a powder that's prismatic?
Yeah, so right now we are limited to spherical particles with our DEM code. We do have some of our users that are using open source DEM or maybe developed in-house. And then really any DEM code that you can convert the result into an STL can be imported into Flow3D AM to do the melting simulations. So we do have some customers that are doing that, but they're not using our DEM to do the non-spherical powders.
Got it, okay. Is it possible to include an inert gas into the laser bed powder fusion simulation?
Yeah, so the way that, because we're dealing with computational fluid dynamics, you're not really, the atmospheric conditions are entirely up to you. And the way that we model these processes is we don't actually fully solve the CFD equations on the gas side of things. So it can be treated as an inert gas. In most cases it is. And then if you have an additional shielding gas pressure, that can also be accounted for.
All right. How does your simulation software take inputs from a novel alloy composition? And do you require a full alloy chemistry yield and elongation?
Yeah, so we what we're mostly looking at is the thermophysical material properties. So we're looking at temperature dependent surface tension, viscosity, density, the phase change properties, lane heat of vaporization, things like that. And for novel alloys, typically what we'll do, or the customer will do, is send the chemical composition over to a database. So JMAT Pro, Thermocalcs, somewhere like that. And then you can get those properties from them. And then when you put it into the software, you're just putting in tabular values of these different properties dependent on surface tension. So you can import it as a CSV, you can put it in manually, but that's how we handle the material properties.
All right. What is the main use of the shielding gas in modeling, apart from additional pressure?
Yeah, so typically, well, in a directed energy deposition, for example, you have a lot of powder particles that ideally are getting melted onto the substrate, but in reality, not all of them are going to be captured that way. So the shielding gas is typically there to protect the optics from powder particles that are flying out of the melt pool that maybe aren't getting melted. And then, additionally for additional melt pool stability. But typically, I think the protective mechanism is the most common reason that it's used.
Here's an interesting one. I mentioned our talent side of the house. How can a beginner, bachelor student or master's student learn the software to do these kinds of simulations more easily?
Mm-hmm. Yeah, so we, as I mentioned, there's a lot of interest in academia. So we do, of course, sell licenses to universities. We also host workshops that are on our website. I think they're bi-monthly right now. But so how that works is you would come in, we would do like a half-day training virtually. You have training videos if you purchase the software. So you get kind of the basics of setting up laser powder bed fusion simulation or a DED simulation. So it's not terribly difficult to pick up because you don't need to understand what's happening under the hood on the numeric side of things. Really just having a good understanding of what your process is and what those inputs are is kind of the requirement. But there's different ways that we offer for students so they can learn the software.
Yeah, I was excited to have a student chime in. That's or someone representing a student. That's that's great. In the DED mode, can someone add nozzle or gas inputs, shield coverage area, and the effects of those?
So in terms of the nozzle, there's typically what we'll do is it's a particle source as we define it. So they're Lagrangian particles, but they can be melted, and then they add that mass and volume into the melt pool once they're melted. You can use a geometry if you want to, and you can put the particle source inside of an actual CAD geometry, which you can import into the software. But typically we just want to know, the angle at which the powder is coming in at, the carrier gas velocity, any initial temperatures, the size distribution. So that's typically how we capture the DED process.
Similarly, you mentioned the carrier gas. So this may have to be taken offline. Actually, are there any images about that show showing carrier gas and shield gas and coverage area in the DED or inner shield gas effects?
Shield gas effects. Well, I would point you to the first study, that DED study that I pointed out from DTU, because what they were looking at was the effect of the carrier gas on the melt pool dynamics. Now, because we're not actually modeling the gas explicitly, we're just accounting for it by various mechanisms, whether it be an additional pressure force or prescribing velocities to the powder feed. So typically, with a DED process, you have a carrier gas that's pulling the powder at a certain velocity into the melt pool. In computational fluid dynamics, we'll just prescribe certain velocities on those particles, which represents the velocity of that carrier gas. The carrier gas is inert, so there really shouldn't be too much of an effect from it anyways. And then the shield gas would be that additional pressure force. So I would say if you can go back into the presentation, I think it was maybe middle of the slide, I linked to all the papers in the case studies that I showed, and that one you can go ahead and read it and see how they accounted for that.
We've got are recording this. Will have recorded this, whatever tense you want to. You might be watching this later, so we did record this, and it's on our website a little bit later on today, so you certainly can revisit some of those. Maybe one or two more. What material properties are needed as inputs and is reflectivity for particular laser wavelengths considered?
Mm-hmm. So the material properties are going to be surface tension, viscosity, density, thermal conductivity, specific heat. So there's some solidification properties, there's some material properties, there's some phase change properties. So those are what we input. So if you typically, for common alloys, these are easily found in literature. If they're not, if it's a more novel alloy, you do tend to have to go to one of these databases that can develop these based on the chemical composition. And then, sorry, Joe, remind me of the second part of the question.
I think hang on, let me find it.
Material
is reflectivity for particular laser wavelengths considered?
Yeah, so the way we deal with the laser is that we'll define the profile of the beam, and then in terms of the absorption, the way that which relates to reflectivity, right? The material is not going to entirely absorb the energy from the laser. So that can be input into the software. Usually it's around 30%, generally speaking. Some materials are different than others, and you can actually input the absorption tabularly too, because you are probably going to see higher absorption once you get into a molten state versus solidified. So that's how we account for absorption and reflectivity.
All right, I know there are a couple other questions that are longer, but I'm going to be sure to share those with Lisa. We can follow up. She can follow up with those offline, and we are running out of time. So I do want to thank everyone for joining today. I want to thank Elise for her presentation. Thank Flow 3D for their membership. And I mentioned materials, process, and systems. Now you can see why they are part of the Lyft team. So we're very happy to have them. So please follow up with her if you have any additional feedback or questions as well. I also want you to stay tuned to your emails for future webinar presentations. On April 12th, we have VRC Metal Systems coming up, and then Solvus Global coming up at the end of April as well. So stay tuned for those. In the meantime, thank you so much for your presentation today, Elise. Thank you so much for everyone joining, and we will talk to you next time. So thank you again.
Thanks, Joe. Thanks, everyone.
All right, talk to you soon.
Bye.